Now we are going to study about magnetic field. Okay, yes, let's see one activity. Okay, now spread some iron fillings collected from the sand uniformly on a sheet of white paper. Okay, which is placed on the table. Now place a bar magnet below the white sheet. Okay, then gently tap the table. Now you can see the pattern as shown in the figure. Yes, like this we can be seen. So what we have to do, first we have to spread some iron fillings which is collected from the sand, and you have to place it uniformly on a sheet of white paper which is placed on the table. Okay, now place a bar magnet below the white sheet. So below the white sheet you have to place a bar magnet. Now gently tap the table. So now we have to gently tap the table. So what we can see from this means we can see the pattern. Okay, and like this, like the figure, it you can be seen the see the pattern. Okay, so from this what we are observing that the iron fillings are arranged in the form of curved patterns around the magnet. Yes, see, it's arranged in the curved pattern only. Oh, see, it's and all arranged in the curved pattern. So we can from this experiment we can say that iron fillings are arranged in the form of curved patterns around the magnet. So the space around the bar magnet where the arrangement of iron filling exists represent the fields of influence of the bar magnet. So the space around the bar magnet. Okay, so this is the space around the bar magnet where the arrangement of iron fillings exists represent the field of influence of the bar magnet. So this iron fillings only will represent the influence of bar magnet. Okay, it will influence the bar magnet. So which is what called as the magnetic field. So the space around the bar magnet where the arrangement of iron fillings exits represent the field of influence of the bar magnet. So that field is called as the magnetic field. So the magnetic field is defined as the space around the magnet in which its magnetic field or influence is observed. So what is magnetic field? It is defined as a space around the magnet. So the magnet in the magnet around it is defined as a space around the magnet in which the magnetic effects or influence is observed. Okay, so space around the magnet is said to be defined as the magnetic field. So the magnetic field is measured by the unit Tesla or Gauss. Okay, yes. Okay, now let's see the tracing of the magnetic field. Okay, okay, we can trace the magnetic field with the help of a compass needle. Okay, with the help of the compass needle we can trace the magnetic field. Now a white sheet of paper is fastened on the drawing board using the board pins or sellotape. So using the board pins or sellotape the white sheet of paper is placed. Okay, now a small plotting compass needle is placed near the edge of the paper. Okay, so now in the edge of the paper a small plotting compass needle is placed and the board is rotated until the edge of the paper is parallel to the magnetic field. So the board is rotated till the edge of the paper is parallel to the magnetic field. So now the compass needle is then placed at the center of the paper and the ends of the needle. Then at the center of the paper a compass needle is placed and at the end of the needles. Okay, so that is the new position of the north and south pole are marked when the needle comes to rest. So that is the new position of north and south pole which are marked when the needles come to the rest. Okay, now these lines are joined and a straight line is obtained. So when these lines are joined one straight line will be obtained. That line will represent the magnetic meridian. Okay, so that line will represent the magnetic meridian. Cardinal direction, that is NESW, which are north, east, south, west, are drawn near the corner of the paper. Okay, cardinal direction we are drawn at the corner of the paper. Okay, so now a bar magnet is placed on the line at the center of the paper. Okay, so now the bar magnet is placed at the center of the paper with its north pole facing the geographical position. Okay, like facing the north pole in the geographical position, a bar magnet is placed on the line at the center of the paper. Okay, now the outline of the bar magnet is drawn. Now one outline of the bar magnet will be drawn. Now take that bar magnet. The plotting compass is placed near the north pole of the bar magnet and the end of the needle is marked. So the plotting compass will be placed near the north pole of the bar magnet and the end of the needle is marked. Okay, so no, the compass is placed in the north pole side of the ball magnet, and at the end of the needle we should put one mark point. Okay, so now the compass is moved to the new position. Now make the compass to move in a new position such that its south pole occupies the position previously occupied by its north pole. So here the south pole will occupy the position. Likewise, previously the north pole occupied the position. Okay. So in this way it is proceeded step by step till the compass is placed near the south pole of the magnet. So from the north pole only we all know it will travel from north pole to the south pole. Okay. So in this way you have to proceed by step till the compass will place near the south pole of the magnet. Okay. So now the deflecting points are marked. So now we have put mark now at the end of the needle we mark no. So now we are that points are marked. Now a curve line is drawn by joining the plotted points marked around the magnet. So now the line is drawn. What line is coming? A curve line is then drawn by joining the plotted points marked around the magnet. When we join the plotted points marked around the magnet, we get a curve line. Okay, so this line represents the magnetic lines of force. So that line is called as the magnetic lines of force. See here we have seen in the picture we can see curve line is drawn by joining the plotted lines. So this line is represented the magnetic lines of force. So in the same way several lines of force are drawn around the magnet. So like that several lines of force are drawn around the magnet. So these curved lines around the bar magnet will represent the magnetic field of the magnet. So these curved lines which are drawn around the bar magnet will represent the magnetic field of the magnet. So the direction of lines is shown by the arrow. Okay, so the direction of line is showed in this arrow. Okay, yes, what we have seen now, a bar magnet is placed at the center of the paper with its north pole facing the geographical north. Now the outline of the bar magnet is drawn. Now then the plotting compass is placed near the north pole of the magnet and the end of the needle is marked. Okay. Now the compass is moved to a new position such that the south pole will occupy the position previously occupied by its north pole. Okay. In this way, you should proceed step by step till the compass will place near the south pole of the magnet, till the compass reaches the south pole of the magnet. Okay, now the deflecting points are marked. So the curved line is then drawn by joining the plotted points marked around the magnet. So this lines is represented as the magnetic lines of force. So in the same way several magnetic lines of force are drawn around the magnet. So these curved lines around the ball magnet represent the magnetic field of the magnet. Okay, these all curved lines around the magnet is represented the magnetic field of the magnet. So the direction of lines is shown by the arrow. Okay, so this is the tracing of the magnetic field. Now we can observe that the compass needle gets deflected to the large extent when it is closer to the magnet. So when the compass is closer to the magnet, we can see that the deflection will be at the large extent. Okay, so when the distance is large, the deflection of needle is gradually decreased. So when there is a large distance, the deflection of the needle will be decreased. Okay, so one particular position there will be no deflection because there is no magnetic field at this position. Yes, the deflection will be decreased. Now if we kept in the large distance, the deflection of the needle will be decreased. So at one particular position, that is if we keep the compass very long distance, then at particular position there will be a no deflection because there will be a no magnetic field at that point. So this shows that each magnet exerts its magnetic influence around a specific region. So this is what shows that each magnet will exhibit its magnetic influence around a specific region. Yes, I hope you all understand. Okay, now let's see that experiment. Now I explain. No, let's see that clearly. Okay, in a video.
Take a small compass and a bar magnet. Note that the red end of the magnet is the North Pole and blue end is the South Pole. Place the magnet on a sheet of white paper fixed on a drawing board and mark the boundary of the magnet. Place the compass near the North Pole of the magnet. The South Pole of the needle points towards the North Pole of the magnet, and the North Pole of the compass is directed away from the North Pole of the magnet. Mark the positions of the two ends of the compass needle. Now move the compass to a new position, such that its South Pole occupies the position previously occupied by its North Pole. In this way, proceed step by step till you reach the South Pole of the magnet. Join the points marked on the paper by a smooth curve. This curve represents a field line. Repeat the same procedure and draw as many lines as you can below and above the magnet. You will get a pattern of lines. These lines represent the magnetic field around the magnet. These are known as magnetic field lines.
Yes, I hope you all understand. Yes, okay. Yes, do you all know that a compass needle, also known as a plotting compass or magnetic needle, okay, which consists of a tiny pivoted magnet in the form of a pointer, which can rotate freely in the horizontal plane. So it consists of a what? Tiny pivoted magnet in the form of a pointer, so it can move freely in the horizontal plane. The end of the compass needle points approximately towards the geographical north and the south direction. So the end of the compass needle will point towards the geographical north and south directions. Okay. Yes. Now let's see about the magnetic materials. Okay. So materials which are attracted by magnet are called magnetic materials. What is magnetic material? The material which are attracted by magnets are called magnetic materials. Okay. The materials which are not attracted by magnet are called non-magnetic materials. Okay, the material which are attracted by magnet is called magnetic material, and the material which do not attracted by magnets are called as non-magnetic materials. Okay, so there are number of materials that can be attracted by magnets. Okay, so there are many materials which are attracted by magnets. These can be magnetized to create permanent magnets. Okay, so the magnetic materials can be categorized as magnetically hot or magnetically soft materials. So the magnetic materials can be categorized as magnetically hot or magnetically soft materials. So the magnetically soft materials are easily magnetized. Okay, the hard materials also, that is magnetically hard materials, can also be magnetized, but they require a strong magnetic field to be magnetized. So like soft magnetized material, it soft magnetic materials are easily magnetized, but hard magnetic materials also can be magnetized, but they require a strong magnetic field to be magnetized. But in soft material they don't require a strong magnetic field to be magnetized. Okay, it is because material have different atomic structure and they behave differently when they are placed in the magnetic field. So because it have a different atomic structure and they will behave differently when they are placed in the magnetic field. So based on the behavior in a magnetic field, they can be classified as below. What they are classified as? They are classified as diamagnetic materials, paramagnetic materials, and then ferromagnetic materials. So let's see briefly about this magnetic field. Okay. First, let's see about diamagnetic materials. So diamagnetic materials has the following categories. Okay. So when suspended in an external uniform magnetic field, they will align themselves perpendicular to the direction of the magnetic field. So when they are suspended in an external uniform magnetic field, they will align themselves perpendicular to the direction of the magnetic field. So they will have a tendency to move away from the stronger part to the weaker part when suspended in a non-uniform magnetic field. Yes, when when they are suspended in a non-uniform magnetic field, they will have a tendency to move from the stronger part to the weaker part. They get magnetized in the direction opposite to the magnetic field. So they will get magnetized in the direction which is opposite to the magnetic field. So the example of diamagnetic materials are bismuth, copper, mercury, gold, water, and hydrogen. So these are all some examples. The magnetic character of this substance is not affected by the external temperature. So the magnetic character of the diamagnetic materials will not affected by the external temperature. By external temperature, it won't get affected. Okay. Yes. Next, let's see about paramagnetic material. So paramagnetic material means when it is suspended in an external uniform magnetic field, they will align themselves parallel to the direction of the magnetic field. So in diamagnetic, what we have seen, when it is suspended in the external uniform magnetic field, they will align themselves perpendicular to the direction of the magnetic field, and in the paramagnetic material, they will align parallel to the direction of the magnetic field. Okay, so they have a tendency to move away from the weaker path to the stronger path when suspended in a non-uniform magnetic field. So when it is suspended in a non-uniform magnetic field, they have the tendency to move up from weaker part to the stronger part. In diamagnetic, what we have seen, they have tendency to move away from the stronger part to the weaker part. Here they are moving from weaker part to the stronger part. Okay, so they get magnetized in the direction of the magnetic field. So they will get magnetized along the direction of the magnetic field. Whereas in diamagnetic material, we have seen they get magnetized in the direction opposite to the direction of the magnetic field. Okay, so some of the example of paramagnetic materials are aluminum, platinum, chromium, oxygen, and iron. Okay, so the magnetic character of the substance is affected by the external temperature. So here the magnetic character will be affected by the external temperature, but in diamagnetic materials they won't affected by the external temperature. Okay, yes. Next, let's see about ferromagnetic materials. So here, when suspended in external uniform magnetic field, they will align themselves parallel to the direction of the magnetic field. Yes, likewise paramagnetic materials, ferromagnetic materials also will align themselves parallel to the direction of the magnetic field. So here they have the tendency to move quickly from the weaker part to the stronger part when suspended in the non-uniform magnetic field. Okay, so they get strongly magnetized in the direction of the magnetic field. In paramagnetic materials, they will get magnetized in the direction of the magnetic field, but here they will get strongly magnetized. Okay, so here the examples are iron, cobalt, nickel, steel, etc. So here the magnetic character of the substance is also affected by the external temperature like paramagnetic materials. So the ferromagnetic materials, when they are heated, they will become a paramagnetic materials. So paramagnetic materials and ferromagnetic materials are somewhat same. Okay, whereas diamagnetic material is different from paramagnetic and ferromagnetic. So in ferromagnetic, when we heat it, they will become paramagnetic materials. Okay, yes, I hope you all understand diamagnetic materials, paramagnetic materials, and ferromagnetic materials. Yes. So the temperature at which the ferromagnetic materials become paramagnetic material is called the Curie temperature. So what is Curie temperature? The temperature at which the ferromagnetic materials became the paramagnetic materials is called the Curie temperature. Yes, I hope you all understand. So now today what we have all seen, We have seen magnetic field and tracing the magnetic field. Then we have seen magnetic materials and the three classification of magnetic materials, which are diamagnetic, paramagnetic and ferromagnetic materials. Yes, thank you.